Can you please, yeah.
Yes, of course. Of course. Okay. So we were talking about the different phases. We did the analysis of the first three phases. If we have, what are the type of heat transfer or work transfer we have? So we illustrated that during compression, we should put a work on the system. During expansion, we produce work. Okay, and so this is W dot compression. So this is W dot expansion. We have energy is released within to the system due to combustion. So you have Q dot combustion that is coming in, and because of the exchange processes, admission and exhaust, we can model it as heat rejected during the exhaust phase. Okay, exhaust admission phase. So we have a heat rejected. So now, okay, let us say Q1 is the combustion energy, Q2 is the rejected energy. We have that if we want to apply Newton, the first law of thermodynamics here, we have that sum Q dot equals to W net, the total, if you want, the net work produced by the system, because we said that a part of the delivered expansion work will be used for compression. So the net will be W dot expansion minus W dot compression, and it will graphically represent the area limited by this curve. Please, if anything is not clear, let me know. Is anything not clear until this equation? Okay, so now if I do the balance of heat, I have plus Q1 minus Q2 equals to W dot. Here, whenever you use this equation, which is the convention you are considering? The convention you are considering for heat, everything coming in is plus, everything getting out is negative. However, because you are putting sum of Q dot equals sum W dot, so for W dot, you are using the opposite convention. Every work that is produced by the system is positive. Every work rate that we put on the system is negative. So it's plus W dot expansion and minus W dot compression. Okay. Now, if I ask you, what is the efficiency of this system? In general, when we talk about efficiency, efficiency is defined by what?
It's how much energy it's producing over the energy you're giving it.
Very good. It's how much energy you are producing over the energy you are putting on your system. Here, in terms of these fluxes that I presented on my figure, what is my input? What is my output? So efficiency in general is output over input. Okay. What is my output here? What do I deliver? What is my net production in this cycle? So I'm transforming combustion into mechanical energy. Okay. This mechanical energy can be quantified by what? Which parameter? You are producing work in this problem, okay? Your purpose is to produce work. So your output is the net work delivered by the system, okay? So your output here is equal to W dot net, which is the network I am able to produce, which is given by W dot expansion minus W dot compression, okay, which is equal as graphically to this area. This is your output, because your purpose is to produce work, to transform the heat energy of combustion into a work that will be used here to rotate your crankshaft, and your crankshaft rotation will be transmitted to wheels, and these wheels will run your car, okay? So your output is the work produced by your internal combustion engine system. Now, what is your input? What is the energy you are consuming?
Combustion.
Very good. Here you are using combustion, and you are burning fuel in order to produce thermal energy. This is your input. So your input is Q1. Okay. Of course, you will not have 100% efficiency. Why? Who can tell me why you cannot get 100% efficiency?
Energy loss.
Due to energy rejection. You were not able to use, and this is one of the laws also. I can never extract 100% work from a certain amount of energy. I will always have to reject a certain part and profit from another one. How you can make your system more efficient? You can make the rejected heat useful. This is what we call heat recovery. Okay? When you have heat recovery, the waste heat is used somewhere else. So I consider then that this is a way of increasing my efficiency, because it's true that within my just my internal combustion engine system, I was not able to profit from it, but I can use it. So my exhaust gases, I can let them pass, for example, through a heat exchanger and exchange heat with air that are getting inside. And instead of admitting air at very small temperature, then I can increase the temperature of admission by using heat transfer from exhaust gas to admission gases. And in this way, I will benefit from a part of my waste energy. This is what we call the heat recovery process. And heat recovery is one of the main strategies to improve the efficiency of my system. Okay. So my efficiency, I can symbol my efficiency like this. This is a symbol of efficiency, is W dot net over Q1. So from my thermodynamic law, what is W dot net? It's Q1 minus Q2. Okay, so my efficiency will become Q1 minus Q2 over Q1. So this is equal to Q1 over Q1 is 1 minus Q2 over Q1. So this is the expression of my efficiency. Now I can get an expression that is related to the parameters of my thermal engine, and we'll see together how. Okay, so I can simplify much more this equation to get the efficiency function of parameters of my combustion engine, and we'll see how to do it now. Okay, so let me try to express the efficiency function of parameters of my internal combustion engines. In general, whenever I have an internal combustion engine, will provide you with some important characteristics. For example, the first characteristic is, if you want, the compression ratio. We call it compression ratio. It relates the ratio of maximum volume to the minimum volume, because during compression process, you move from point A, which is beginning of compression, to point C. And we can say that the volume corresponding to point A, let's call it VA, and the volume corresponding to point C, let us call it VC. And we define one of the characteristics of a motor is the compression ratio, epsilon. So we can define epsilon as VA over VC, and we call it compression ratio. Okay, so this is called the compression ratio. And of course, if I give you any problem such this, like this, I will define for you all parameters. But I can tell you, express the efficiency function of the compression ratio given by VA over VC and other parameters that I specify for you. And you should, from your knowledge, put the equations and try to find the efficiency. So this is the compression ratio. Okay. And also, another parameter that is characteristic of adiabatic phases is the following one. In any adiabatic phase, as you have seen in the course material, you can write an equation. Adiabatic phase is characterized by the following equation. Pressure times volume to the power K is a constant. So whenever I tell you that you have an adiabatic phase, you can say that the equation driving this phase is the one relating pressure and volume, which is PV to the power K equal to a constant. Okay, so all you need is to know K. K is a characteristic of the fluid. So let's say for air, we have certain values of K. For other fluids, we can have different values. So K in general is given for you. So my question is, try to find the efficiency function of epsilon and K only. Okay, this is what I will try to do. To be able to do this, I should go back to my, if you want, equation, which is the efficiency is 1 minus Q2 over Q1. But what is Q2 and what is Q1? So let us go back to physics that can give us Q2 and Q1. Okay, we said that Q1 is the energy gained from combustion. But we modeled the combustion process as a constant volume process. Okay, and here we'll take the assumption of ideal gas. So we will treat the fluid as an ideal gas. Okay, for a constant volume process, who can tell me what is the equation of an ideal gas for a constant volume? First, do you remember the ideal gas law? The ideal
PV
gas
equal
law.
an RT.
Yes, the ideal gas. Whenever I tell you can treat a gas as ideal gas, this means that you can write that pressure times volume equals to N times R times T. Okay, where N is the number of kilomoles circulating, and it's a constant for a closed cycle here. We are considering that, we said, we are considering a certain mass circulating in this cycle, no change in mass, so no change in number of kilomoles. Okay, so N is constant. So if so N is constant, R is what we call the universal gas constant, it's constant. And for a isochoric process, for a constant volume process, V is also constant. So what can you deduce about a constant volume process? For a constant volume process, pressure over temperature is constant. is not varying. Okay, so I can say that for if I take the two limiting points, so if I call this point A, this is C, let's say, this is point Z, for example, and this is called B. Let's say I use these names for the extreme points. Okay, because P over T is constant for this process of combustion, then I can write that PZ over PC or PZ over TZ is equal to PC over TC. Okay, so let me, if you want, I will draw a graph that will not be erased, so it will remain for you, and then we write the equations, we can erase them. So this is our graph again. So we called this point A is beginning of compression. This is point C, end of compression. This is end of combustion. And this is point B, corresponding to end of expansion. Okay, now we said that during this phase P over T is constant, so I can write that PZ over TZ is equal to PC over TC. Okay, now Q1, which is the heat gained during this process. Do you have an idea how can I express it? Function of my temperatures. What is the expression of heat exchange at constant volume? It's one of the formulas in this chapter. I will remind you of the formula. Q1 is m dot Cp delta T. Okay, so Q dot 1, which is the heat rate, is m dot, which is the mass flow rate circulating, times the specific heat at constant volume. So whenever you have heat exchange at constant volume, you use m dot Cv delta T. Whenever you have exchange of heat at constant pressure, you use m dot Cp delta T. Cv or Cp, when you have a constant volume, Cv is the specific heat at constant volume, and Cp is the specific heat at constant pressure. So here, since this process is taking place at constant volume, I can express the heat exchange as m dot Cv delta T. So Q dot 1 is m dot Cv delta T 1 in phase 1, which is Q dot 1 equals to m dot times Cv. Now the difference in temperature between points Z and C is Tz minus Tc. Okay, so this is, I can see that Q is related to the temperatures. So I will write my ratio to determine what is the ratio of temperature I need to get my efficiency. Let us find together the expression of Q dot 2. So we have heat rejection at this stage here. Okay, so Q dot 2 will be equal to m dot. Also, this process between A and B is taking place at constant volume. So it's m dot Cv times temperature at point B minus temperature at point A. Okay, and we have seen together that the efficiency is 1 minus q dot 2 over q dot 1. So it's 1 minus m dot cv times tb minus ta over m dot cv times tz minus tc. Okay, so now I can simplify m dot and cv, and then to get my efficiency formula I need to determine this ratio of temperatures. Okay, and look, whenever you have to derive a formula in such problems, think about introducing ratios, because ratios can be related to general parameters. Okay, while if you keep them like this, you cannot do any simplification. You need to know what is TA, what is TB, what is TC, and what is TZ to solve for the efficiency. However, if you appear ratios, you can express these ratios function of your characteristics or the characteristics of your engine, and this will allow you to get a simplified expression for your efficiency. How can I figure out ratios here? It's very simple. All I have to do is to take a certain temperature of interest into factor. Okay, look, we said that, what do we know? What is the characteristic we want to try to implement? Epsilon. Epsilon is VA over VC. Okay, and because this is an adiabatic process, I can relate the ratio of velocities to the ratio of temperatures. So keep in mind, in adiabatic processes, I can relate ratios of velocities to ratio of pressures and to ratio of temperatures. Now we'll see how. Okay, so it's of interest for me to appear in my relation the ratio TA over TC. This is what I will try to do. To appear this ratio, okay, I can take in my numerator TA into factor, and in my denominator TC into factor. So what do I get then? My efficiency is, as we said, 1 minus TB minus TA over TZ minus TC. Let me try to figure out this ratio. So I will take in my numerator TA into factor. I get 1 minus TA times TB over TA. So I just here take TA into factor. So I get inside my brackets TB over TA minus 1. And in the denominator, I will take TC as factor. So I get over TC times TZ over TC minus 1. It might seem complex now, but you will see that it will simplify a lot after. Okay, sorry, here 1 minus is outside. Okay, it's outside of the fraction, so it's here 1 minus this fraction. So you can say that I transformed my efficiency parameter function of 3 ratios, which are TA over TC. So if I determine the ratios TA over CC, TB over TA, and TZ over TC, I will be done. I can get an expression, a simplified expression for my efficiency. Okay, how to do this? Let us try together. Okay, first, TA and TC are joining these points, and these points belongs to an adiabatic process. Okay, an adiabatic process is characterized by several relations. You can say that PV power K equal constant. You can say that TVK minus 1 equal constant. You don't have to memorize all of these. You know why? it's enough to know one relation. If you know just that P times Vk equal constant, and you use the ideal gas law, the ideal gas law is PV equal nRT, okay? And we said for a certain quantity of fluid circulating, nR is a constant, okay? So if I substitute pressure can be substituted by a constant times temperature over volume, okay? So replace here, plug instead of P a constant. Of course, this is constant 1, this is another constant 2. So I can lump constants together. I lump constants into one constant value. And I say if I replace P by T over V, I get the following. I get T times V to the power K over V is equal to another constant. So now, by simplifying here 1V, I get TV to the power K minus 1 equal constant. So for an adiabatic process, you can use this relation between pressure and volume, but also you can use this one between temperature and volume. So this will help you to relate TA and TC. Why? Because A and C are 2 points of an adiabatic process. So now you can use this relation to relate their temperatures. You can say that at point A, I have TA times volume at A to the power K minus 1 is equal to TC times volume at C to the power K minus 1. And now I will appear this ratio. I take TC to this side. So I get that TA over TC is equal to VC over VA to the power K minus 1. And going back to your characteristic epsilon, what is epsilon? Epsilon is the inverse of this. It's 1. Epsilon is VA over VC. So I deduce that TA over TC is equal to 1 over epsilon to the power K minus 1. And then I am done with my first ratio. I was able to express this ratio function of parameters that are general parameters given for me for any motor, which are epsilon and K. Okay, so now once I am done with this ratio, I try to figure out a relation between these two ratios, TB over TA and TZ over TC. And you will see that these ratios are equal, and we'll demonstrate this together. Okay, so now we still have to find a relation TB over TA in relation, or we can express it and find what is TZ over TC. If you just have a small look at your points, you can profit from the fact that the volume at B and A are equal. So VA is equal to VB. And if you look at Z and C, they have equal volume. To profit from this, all you have to do is to write the relations of your two adiabatic processes here, this one and this one. So from adiabatic relations, okay, what do you have? Between A and C, you can write that. We have seen that for adiabatic process, TVK minus 1 equal to a constant. Okay, so I can write that TA times VA to the power K minus 1 is equal to TC times VC K minus 1. And I can do the same procedure for the other adiabatic process between B and Z. So between B and Z, I can write that TB times VB to the power K minus 1 is equal to Tz times Vz to the power k minus 1. And then to profit from this idea that the volumes at A and B are equal and the volumes at C and D are equal, this is relation 1, this is relation 2. Let us divide 2 by 1. If we do 2 over 1, what will happen is that VA, VB will cancel out and VC, VZ will cancel out. So I will get that the ratio of TB over TA is equal to the ratio TZ over TC, which is great because this will simplify a lot the expression of my efficiency. Okay, now going back to my efficiency equation, I will end up with a very simple result that the efficiency we said is 1 minus TA over TC. And if you remember, it was multiplied by I think it was TC here minus 1. Let me check. It was Q2 over Q1, okay? And the Q2 is TB minus TA. Okay, yes. So it was because you had before TB minus TA over TZ minus TC, okay? And you took into factor here TA. So you have here TV over TA minus 1 over TZ over TC minus 1, okay? So we've demonstrated together now that these two ratios, TB over TA and TZ over TC, are equal. So these two terms will cancel out, they will simplify, and you will end up with your efficiency equal to 1 minus TA over TC. And we have demonstrated together that this ratio, TA over TC, is equal to 1 over epsilon to the power k minus 1. Okay, so you were able to get a simple form of your efficiency. Your efficiency is function of the compression ratio, and from here you can give recommendations to enhance the performance of your motor. Higher your compression ratio, if you look at this equation, higher is epsilon, lower is higher is your efficiency, because higher is epsilon, then lower is this number, and since you have minus before it, so higher will be your efficiency. So it's a good strategy to increase the compression ratio of a motor, of an engine, in order to increase its efficiency. Okay, so this was one practical example on the different concepts introduced in this chapter. Any question on this? I will try to give you some additional practical problems like this, so you can try to do them and we can correct them together. And as usual, I will assign for you some videos to watch during this week. Okay? Any question before we stop? Thank you for your time. Bye-bye.
Thank you.
Thank you.